Welcome to Smith Chart Part 2. We've kind of started the motivation in Part 1. This part is going to be getting into the weeds of the algebra, which is not really covered in the text. So here we go. We know at the load that the input impedance, Zn, is going to be equal to 1 plus gamma over 1 minus gamma. And the value gamma in general is complex, so it's a complex number. As we mentioned before in the introduction, we want to know what it is at any z. At any z, what's the input impedance? So what happens, and these are all normalized, there's no z naughts here, it's a pure number. So these are normalized input impedance. So we're taking the load, for example, and dividing it by the characteristic impedance of the transmission line. So in general, Zn is going to be what? What's the difference? Well, the difference is this gamma is basically modulated by how far we are at the load at any particular distance. So let's put that in. So we got 1 plus. Now, I'm going to actually write in the complex form of gamma. There it is. Now, we're going to have e to the j. We're going to get phi. And at z equals minus L, we're going to get minus 2 beta L. And that's based on the previous algebra that we did. Divided by, the only difference is, remember, voltage, current, minus sign. We spent a lot of time talking about that minus sign. So let's look at what this means. So at the load, we just have Zn is this ratio. Now, as we move away down the line at z equals minus L, we see that the reflection coefficient has an additional phase shift given by this. That means we can view the input impedance away from the load, and then we're going to use that to solve some fantastic problems, but we need to do a bunch of algebra, which is really where we left off before. And the other way to think about this thing here, just conceptually, the books really don't give you the motivation of where that rotation comes. So if I look at gamma here, that's a complex number. So let's draw it on the circle. Center of that circle is in the impedance plane. Complex plane is sitting here, 1. And there's my gamma, and there's some angle, phi. So there's gamma, and the radius of this circle can't be bigger than 1. It could be less than 1, but can't be bigger than 1 because you can't have a reflection coefficient bigger than 1. Now, as we move down the line, let's say L is positive. So minus 2 beta L, that phase got a minus sign, so it's clockwise rotation. So clockwise is this way, going around with the clock. So as we move down the line around the clock, from the load to the generator, we're moving clockwise. And what we're going to see is we'll be able to compute what this Zn is at any point as we move. So that's what we're going to do. So what we have to do is do a whole messy algebra business. Now, in order to simplify it, I'm going to look at this term, and I'm going to write it as gamma real plus j gamma imaginary. And the same down here. And then z in normalized is going to be r plus jx. Normalized resistance, normalized reactance. So now it's time for doing the algebra. So the next boards, as I go, I'm going to fill this board up. We're going to have to erase, and I'm going to carefully go through one of the algebras. The other one we are going to do in class as practice with complex numbers. So let's do it. We have to find the real and imaginary parts of this expression. So this is a real challenge. I better start over here right at the edge of the board. R plus jx equals. Going to call this whole thing so the top becomes 1 plus gamma real plus j gamma imaginary divided by, this is just messy. I mean, you have to do it carefully. Gamma real minus j gamma imaginary. Right, so now what do we have to do? Well, I don't have a lot of room, so I have to explain what I'm doing as I write. We multiply top and bottom by the conjugate. Okay, so what's the conjugate of this? 1 minus gamma r, that's the real part, plus sign. 1 minus gamma r plus j gamma imaginary times the same thing below, gamma r plus j gamma imaginary, which is equal to. Now, this is not going to be nice because we're going to have 9 terms in the numerator. That's why I hope all 9 terms fit across here. Wow, this is going to be a challenge. So let me see if I can do it. 9 terms. Wow. And the bottom is easy because this is real, that's imaginary. So we know what that is. It's going to be the real part all squared plus the imaginary part all squared. All right, let's do the numerator. I have some notes here because I'm trying to avoid typos, because typos in this are deadly. We're going to go slow. I'm going to do it like this. I'm going to take 1 times all these plus gamma r times all these plus j gamma I times all these. So let's do it. Well, 1 times that is easy. 1 minus gamma r plus j gamma I. That's 3 out of 9 done. Now, the next term is going to be, take gamma r times 1, gamma r times 1. Gamma r times minus gamma r is minus gamma r squared. And gamma r times j gamma I is that, plus gamma r times j gamma I. Can we fit the next 3 terms in? I don't know. So now we have j gamma I times that. And we have j gamma I times minus gamma r, so that's minus j gamma I times minus gamma r. J gamma I times minus gamma r, that's the term we're doing. J gamma I, we put the minus sign in, and gamma r. And the last term, j gamma I times j gamma I is minus gamma I squared. Barely did it. Fantastic. Let's count the terms. We've got 9 of them. 1, 2, 3, 4, 5, 6. Wait a minute. 1, 2, 3, 4, 5, 6, 7, 8, 9. Yeah, they're all there. Now, some simplifications happen. Well, some simplifications. We got a minus gamma r and a minus gamma r, so that cancels that. And j gamma I, we got one of those, and we got another one there. So there's 2 of those. And then we have the other terms. Also, the gamma r, j gamma I, we got a minus j gamma r gamma I. They cancel out. So we, in fact, only have 4 terms left. So this cancels that. So we have the cancellations, and these combine. So I'll write it in pink then. It's going to be 1, nothing there, plus this combines with that. That's 2j gamma I. So we've taken care of that. And then we get a minus gamma r squared. So that takes care of that. And we have a minus gamma I squared divided by the same thing below. I'm running out of space, so I'll do it like this in pink. Gamma I squared. Okay. So this pink is equal to this. Now, it's easy to read off the real and imaginary parts. For example, r is going to be equal to, this is always real, so this term, and this term. And there will be a similar for the imaginary. So let's do that on the next board. Well, here we are. This is where the previous blackboard, lightboard full ended up. And now what we're going to do is identify the real and the imaginary parts. Just you can see what r is. I've just taken all the real in the numerator. The denominator is real. X, of course, just has this 2 gamma I divided by the same denominator expanded out. So to give us a bit of room, I'm going to erase this. And then while I'm doing this, I'll tell you what we're going to do. We're going to deal with the real part only and do the algebra and see what we get. It's going to get some interesting stuff. We have to basically cross multiply, collect terms, add something by completing square, and we're going to get a family of circles that depend on r in the gamma plane, in the gamma disk. Remember that that disk has a maximum diameter of a radius of 1, because you can't have a reflection coefficient greater than 1. And also, once we have it, the minute we move away, we're rotating gamma, so we're moving around in complex numbers, and as we move around, we pick up different values of r. So when we do examples, you'll see how cool this all is. So let's cross multiply this, and I'm going to skip a couple of algebraic steps. So when I cross multiply, this is going to be on the right-hand side, and r times all these guys here, and I'm going to rearrange it. So you'll just have to believe my algebra. I'm not just going to multiply right away by this. So r gamma r squared. I'll start with that term. R gamma r squared plus gamma r squared. I'm going to take some of the stuff here and leave. So this gamma r squared comes from here. And then we get minus 2r gamma r. So that's this one cross multiplied there. Then we get an r. Then we get r plus gamma I squared. And I think that's all we get. There should be 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5. Oh, we're missing one. Oh, r gamma I squared. And we got the gamma I squared from the right-hand side. It's equal to 1. Now it's getting more tractable. Believe it or not, we can combine these terms. Gamma r squared into r plus 1. Minus 2r gamma r plus gamma I squared into r plus 1. Got to remember the superscripts go on top. It's not r squared. It's always components of gamma squared. Gamma I squared into r plus 1 is equal to 1, and then I'm taking this r to the other side, 1 minus r. Now, the next step is to divide by r plus 1. So I'll need the towel for that. So this is nice. If we divide by r plus 1, this goes away, and this goes away, and this becomes over r plus 1. And this is 1 minus r over r plus 1. And now we're just about there. If you look at this, gamma r squared minus 2 times something times gamma r. So you know that that's of the form something squared, right? X minus y squared is x squared minus 2xy plus y squared. So the y here, so here's the x. It's like the gamma r, and the y is this thing here. So we can make this a perfect square if we add what? We don't have to worry about the 2. R over r plus 1 quantity squared. We also have to add it to this side. So let's do that. Gamma r squared minus, this stays the same, r plus 1, gamma r. Now we're going to complete the square, so we're going to add r over r plus 1 quantity squared plus gamma I squared is equal to 1 minus r over 1 plus r plus the thing we added, which is r squared over r plus 1 squared. And you'll recognize what? This is a perfect square, gamma r minus r over r plus 1, all squared, plus gamma I squared. You can see what this is. This is a constant. We're going to simplify it in a minute. But these are families of circles for a given r, right? Because this is r is the x component of a vector, I is the vertical one. So this is like x squared plus y squared. X minus a constant squared plus y squared is equal to the constant squared. So let's do that up here because I have room. And to do that, I do 1 minus r. I put this over a common denominator. all squared. That's the first term plus the r squared. And so what is this? This is 1 minus r squared, and it combines with that, and we get, finally, 1 over r plus 1 squared. And these are our family of circles, so this is equal to 1 over r plus 1 squared. And shortly, in the next description, when I bring up some PDFs, we'll see what these families of circles look like. And now in class, and at a future time to be determined by me, you are going to get a practice to do the same for the reactance circles. And that's all we have. Now we have to do that reactance circle, and then I can show you how the things look like when you plot them out, and then we'll use them for some examples.